For 13.8 billion years, our cosmos has operated under one unbreakable, non-negotiable decree. It is a law not written in stone or starlight, but woven into the very fabric of existence. A truth so profound, it governs the life of a star and the cooling of a cup of coffee with equal, unforgiving authority. This is the second law of thermodynamics. It is the universe's solemn promise of decay. It is the formal name for the arrow of time, the reason why an egg, once scrambled, can never be unbroken, and why the past is a fixed memory while the future remains an open sea of possibilities. In the mid-19th century, physicists like Rudolf Clausius gave this cosmic tendency a name: entropy. Entropy is the measure of disorder, of randomness, of energy spreading out until it is useless. Every action, every reaction, every single tick of every clock in the universe generates a tiny, irreversible increase in this cosmic chaos. The second law dictates that the total entropy of an isolated system can only ever increase or stay the same. It can never, ever decrease. This isn't just an abstract equation, it is the ultimate fate of everything. This law is what powers the engine of change, but it is also a death sentence for the cosmos itself. It predicts a future known as the heat death of the universe, a time in the far, far distant future when all the stars have burned out, all the black holes have evaporated through Hawking radiation, and all that remains is a cold, dark, and perfectly uniform soup of elementary particles at a temperature just fractions of a degree above absolute zero. In this final state of maximum entropy, nothing interesting can ever happen again. The universe will have achieved perfect equilibrium, a state of ultimate, eternal rest. The cosmic story will be over. Every clock will have wound down. This is the grand, melancholic narrative of classical physics. The universe's slow decay is not just a possibility, it is an inevitability. For centuries, this principle has been the bedrock of our understanding, a fundamental limit on what is possible. The idea of a perpetual motion machine, for instance, was dismissed not just as an engineering challenge, but as a violation of these sacred laws. Specifically, a machine that could create energy from nothing would violate the first law, the conservation of energy. But a machine that could perfectly recycle its energy forever, never losing any to heat or friction, would violate the second law, as it would fail to increase entropy. And yet, in 2012, a question, both simple and profoundly heretical, was posed by Nobel laureate Frank Wilczek. He looked at the world of crystals, the perfectly ordered, repeating lattice of atoms in a diamond or a snowflake. These are crystals in space. Their structure breaks what physicists call spatial translation symmetry. This symmetry simply means that the laws of physics are the same everywhere. If you move a few feet to the left, gravity doesn't change. But inside a crystal, this symmetry is broken. The space is not uniform. There are atoms here, but not there, in a repeating pattern. Wilczek then asked, if we can have crystals that break symmetry in space, could we have crystals that break symmetry in time? Could a physical system, in its lowest energy state, spontaneously settle into a periodic, repeating motion? A clock that ticks forever without energy input. A system that moves and changes in a perfect, repeating rhythm, not because it's being pushed, but because that rhythm is its natural, most stable state of being. This idea seemed to fly in the face of everything we knew. A system in its ground state, its lowest possible energy level, should be static and unchanging. Any motion implies kinetic energy, which means it can't be at its absolute minimum. A perpetually ticking object in its ground state would be like finding a ball that continuously rolls back and forth at the very bottom of a valley without ever being touched. It seemed to defy the second law's relentless march towards static equilibrium. It was a beautiful, elegant, and seemingly impossible idea. It suggested a form of perpetual motion, a loophole in the universe's most fundamental rule. It whispered of a forbidden rhythm, a pulse beating within the quantum realm that never tires and never fades. The scientific community was deeply skeptical. The initial proofs even suggested such an object was mathematically impossible under equilibrium conditions. It was a phantom in the equations, a ghost of an idea. But physics is not a collection of static truths. It is a process of relentless questioning. Could such a forbidden clock truly exist, or was it merely a theoretical phantom, a beautiful dead end in the search for understanding the ultimate nature of reality? From that theoretical phantom emerges a startling quantum reality, now confirmed in labs from Google to the University of Maryland. The forbidden clock is real. But its existence doesn't shatter the laws of physics. It reveals a loophole so subtle and profound that it was hidden in plain sight within the strange rules of the quantum world. The key insight which unlocked the puzzle was to stop thinking about systems in perfect, isolated equilibrium. Instead, physicists realized that time crystals could exist in a special kind of non-equilibrium state, one that is periodically driven by an external force, like a laser. This is where the magic happens. A time crystal does not violate the first law of thermodynamics. It is not creating energy from nothing. The external drive provides the energy. However, it does something far stranger. It spontaneously breaks time translation symmetry. This symmetry is one of the most fundamental principles in physics. It's the simple, intuitive idea that the laws of nature are constant over time. An experiment performed today will yield the same results if performed tomorrow, all other conditions being equal. It's the foundation of scientific repeatability. A normal everyday object, when you push it, responds in a predictable way. If you push a child on a swing once every 2 seconds, the swing will move with a period of 2 seconds. It follows the rhythm of your push. It obeys time translation symmetry. But a time crystal does not. It takes the energy from the external drive and uses it to lock into a new independent rhythm. A rhythm that is an integer multiple of the drive's period. This is called a subharmonic oscillation. Imagine pushing that swing once every 2 seconds, but the swing of its own accord decides to only reach its peak height every 4 seconds or every 6. It has spontaneously chosen its own, more stable, longer period rhythm. The system remembers the push, but it marches to the beat of its own internal drum. This is the signature of a time crystal. It's a collective emergent behavior where a vast number of quantum particles all agree to oscillate in perfect, synchronized time, but at a frequency different from the one they are being driven at. In 2017, this abstract theory was made stunningly real. As reported in the journal, a team led by Christopher Monroe at the University of Maryland built one of the first confirmed time crystals. Their setup was a masterpiece of quantum engineering. They took a chain of 10 ytterbium ions, each acting as a quantum bit or qubit, and held them in a supercooled ion trap using electromagnetic fields. They then used precisely timed laser pulses to push the system, attempting to flip the quantum spin of the ions. According to classical intuition, the spins should have flipped in direct response to the laser's frequency. Instead, the researchers observed the impossible. The chain of ions settled into a stable oscillation at exactly half the frequency of the laser pulses. They pushed it with a rhythm of tick-tock, and the system responded with a rhythm of tick-tock. It had become a crystal in time, its pattern repeating every 2 pushes from the laser, not 1. Almost simultaneously, a team at Harvard achieved a similar result in a dense arrangement of nitrogen vacancy centers in a diamond. And shortly after, a team using Google's Sycamore quantum processor demonstrated a time crystal using 20 superconducting qubits. This confirmation across multiple, vastly different physical systems proved that the phenomenon was not a fluke or an artifact of one specific setup. It was a new, robust phase of matter. The implications are staggering. This discovery doesn't just add a new chapter to physics textbooks. It redefines our understanding of what stable even means in the quantum realm. One of the greatest challenges in building functional quantum computers is a problem called decoherence, where the fragile quantum states of qubits are destroyed by the slightest interaction with the outside world. A time crystal, however, is an intrinsically stable, self-correcting system. Its rhythmic state is a collective property of the entire system, making it incredibly resilient to small errors or perturbations. This opens up an entirely new avenue for creating more stable quantum computing architectures, where information is encoded in the robust, perpetual rhythm of a time crystal rather than in delicate individual qubits. We have found a clock that is not wound by a spring, but by the fundamental laws of quantum mechanics itself. A clock that is not just a timekeeper, but a new state of being. If time itself can crystallize into a repeating pattern, what other fundamental symmetries of our universe are just waiting to be broken?